let me thank the organizers of this nice event for kind invitation to speak here. It's a very nice place and very nice conference. So the talk I'm going to give is based on the joint work with Alexei Kokotov and Petr Zograf. And actually, there are several papers which I'm going to summarize. The approximate plan of the talk. So the idea would be I'll start from some classical objects which in modern language they belong to the field of integrable systems. But it's classical objects, the systems of ordinary differential equations with meromorphic coefficients. Now that they got some interpretation in the framework of the integrable system theory, I will start from there and then start slowly moving towards determinants of Laplacians. In the end, I will discuss maybe some questions related to ergodic theory, but well, depending on time I have. So, roughly speaking, the plan will be like that. First, I'll talk about so-called Schlesinger systems. Schlesinger system, Riemann-Hilbert problem, and Tao function. That's just the outline, the origin of the objects we are going to work with, because if I would be speaking to people working in integrable systems, I would skip that completely. But somehow there is obviously some interdisciplinary barrier, which, well, for people whose origin is spectral geometry, this topic could be a little bit unknown. So then I will summarize all kinds of variational formulas. On Riemann surfaces. This is basically also the textbook material, but somehow I'll try to consider that from some angle which is probably not very common. Then I'll talk about some special kinds of Riemann-Hilbert problems. Special Riemann-Hilbert problems coming from Hurwitz spaces. Hurwitz spaces and their Tao functions. So these Tao functions already are closely related to the problems of holomorphic factorization of the determinant of Laplacian. And here we will start approaching the determinant of Laplacians. And then fourth will be the Tao functions on spaces of holomorphic differentials over Riemann surfaces and determinant of Laplacian. So here, when I'm going to talk about Hurwitz spaces, as a byproduct, we are going to get some new relations in Picard group of the compactifications of Hurwitz spaces by, well, the so-called spaces of admissible covers, the relations which were known only in hyperelliptic case to algebraic geometers. Here, the formalism of the Tao function, well, basically the Tao function will turn out to be a section of certain line bundle, and looking at its divisor, we can express the Hodge class in terms of the boundary classes of the space of admissible covers. So let me start from this. Well, here you can start either from Riemann-Hilbert problem or from just system. Let's consider the system of differential equations. Lambda is, or let me use z as a coordinate on the complex plane. And here I put sum from 1 to n, aj over z minus zj psi. So I assume here that psi is n by n function, n by n matrix, depending on the variable z. AJs are some matrices. residue matrices. Now, very classical object system of linear differential equations with meromorphic coefficients. So suppose we also impose some kind of boundary condition. Let's assume that psi at z equals infinity. The initial condition will be like that. And to be able to impose a condition like that, of course, we need the infinite point to be a regular point of our system. So we will have to impose the condition that sum of all residues is 0, then infinity is regular, and we can normalize the function like that. So now let's do the following. Let's suppose we consider point on the Riemann sphere, point infinity. Then, of course, we can solve our equation in the small neighborhood of infinity. And then suppose we want to analytically continue it around the singularities. Z1, Z2, etc. By the way, let me use different letters here and here. N big stands for the dimension, and for the matrix dimension, and small for the number of singularities. Zn. Then we start, well, choose some generators of the fundamental group of the punctured sphere and start continuing along these loops. And of course, no one told us that after the continuation, our function should come back, right? So typically, in the generic situation, we get some right multipliers, right? If we denote these loops by gamma 1, etc., gamma n, then if I go around gamma j, then psi gets a multiplier, which is called the monodromy matrix. So, of course, we can look at that as just the monodromy representation corresponding to the flat connection, well, d by dz minus this sum. So, of course, that's not really a representation. It's anti-representation of the fundamental group, because if I multiply the loops from left to the right, well, the relation between matrices is like that. Is m infinity, if this condition is imposed, then m infinity is not there. Mn minus 1, etc. m1 is equal to 1. Now, suppose we want to ask the following question. Given the monodromies, how to restore these residues, or how to restore our function psi? So, suppose we are given a set of monodromies and positions of singularities. So, how to restore the function psi and the residues? It's that where the Riemann-Hilbert problems arise. So this is the inverse monodromy problem. Monodromy or matrix Riemann-Hilbert problem. Well, depending on the formulation, there are various formulations. I can formulate it exactly like that. Then the solution is, of course, highly non-unique because, well, I can in particular multiply function psi from the left with any rational function, and the monodromy representation will remain the same. But I can also add here to this set of data, or to this set of data, the eigenvalues of these matrices Aj, and then the solution will be unique. But then we will lose solvability. It was the quite famous Bollybruch result that if I add also the eigenvalues to this set, then the Riemann-Hilbert problem can be sometimes not solvable. But in this formulation, it's always solvable. Well, still, it's quite non-trivial. All these formulations are related to each other, but not exactly coinciding. Now, let's start look at this picture and start deform with respect to lambda j's, to zj's. So let's start changing the positions of singularities. Of course, we can turn on this deformation in infinitely many ways, but somehow the special role is played by the so-called isomonodromic deformation. Isomonodromic deformation. And this is, well, of course, this name suggests that we impose the condition that monodromy matrices are independent on that case. If you do that, then, of course, the residues gain quite a non-trivial dependence on the singularities. And, well, it's rather easy to check that this condition will imply that derivatives of psi with respect to zj, they are given by the following formula: minus aj over z minus zj times psi. To deduce this equation, we should look at the local behavior of function psi and differentiate it with respect, take the logarithmic derivative with respect to zj using the isomonodromy condition. I am not doing that here because that would be too much. I am, anyway, a little bit too elementary.
Sorry, let me make sure. What is AJ?
AJ is a matrix.
Yeah, what matrix? What matrix?
Of the, well,
how did you write here?
well, I take a set of matrices, arbitrary set of matrices, A1, etc., AN. And each matrix has, well, is a square matrix of dimension n big. So that's it, but for the beginning, right? Okay, so now I got these equations, and let me look at that and the original equation. They have to be compatible. So I have to differentiate this connection coefficient with respect to zj minus this connection coefficient with respect to derivative with respect to z plus commutator should be equal to 0. Right? Standard zero curvature condition. And if I do that, zero curvature, then I get a set of equations governing dependence of the residues with respect to the positions of singularities. They will look like that. dAj by dzk is equal to the commutator of aj with ak over zj minus zk for k non-equal to j, and dAj by dzj is equal to minus sum over k non-equal to j of aj ak over zj minus zk. So this system of equations is called the Schlesinger system and was derived in 1911. So then I don't know. People didn't look at it too much until the works of Jimbo and Miller and co-workers in 1979, 1980, 1981, etc. Well, who realized that the same system arises in the study of the holonomy vector fields. If you, well, so the very simple models of quantum field theory give you this type of equations. And from pure mathematical point of view, forgetting about the quantum field theory and all that, the really important contribution of them was that they introduced the notion of so-called Tao function. So, well, this was known to Schlesinger, but the Tao function was not known. And it's the Tao function which allows to to do a lot with this system. So Tao function, the definition of that is the following. I take a system of equations, d by dzj, logarithm of tau of locally tau is a function, globally it could be a section of a line bundle, of course. It's 1/2 of residue at the point zj of trace of a square of z, where by a of z we denote this sum. Or if you write it in terms of residues themselves, then you get something like that. I'm not sure about the coefficient here. The coefficient is correct here. I'm not sure, but roughly it's like that. Sum over k non-equal to j, trace of aj ak over zj minus zk. So, of course, well, again, there arises a question of compatibility. The connection has to be flat to admit the section, right? And the connection is flat. So if I differentiate this thing, well, take two equations with respect to the j and zl, take second cross derivatives, then I get 0 as a corollary of the Schlesinger system. So compatibility follows from Schlesinger system. What's the mathematical significance of the Tau function? You see, first of all, there is a theorem that the Tau function is always holomorphic in the space of the j's, but outside of the diagonals. If we take the space Cn, take out the diagonals, so we don't allow the singularities to merge, then Tau function is always holomorphic there. It doesn't have poles. It was Jim-Bemeva conjecture, which was proved partially by Jim-Bemeva themselves, partially by Malgrange, partially by Bollebruch. Anyway, so that's a holomorphic object, which is nice. The second thing, well, of course, it can be a section of a line bundle, not a function, and the exact examples we are going to see. Second, what about the divisor of zeros? If you look at the divisor of zeros of Tau, divisor of zeros. So what can we see? If the Tau function has 0, it means that, well, this logarithmic derivative becomes infinite, right? So that means that zeros of the Tau function sit at the poles of the solutions of the Schlesinger system. So the solution of Schlesinger system becomes singular when Tau function gets 0. Now, from the point of view of a Riemann-Hilbert problem, if I formulate the Riemann-Hilbert problem, well, in more rigid way, so if I add the eigenvalues of the matrices Aj to this set, then at the zeros of the Tau function, this Riemann-Hilbert problem becomes unsolvable. So that's the way the zeros of the Tau function is are related to the solvability of the Riemann-Hilbert. If I take this weaker version of the Riemann-Hilbert problem, then also something special happens at the zero divisor, but that probably I am not going to discuss. It was many papers of Bollebruch were devoted to that. Okay. So what else did I want to say about this subject? Probably for the moment I stop here. So my goal would be to use a special version of this object in the context which is of interest for spectral geometry. But for that I have to go some way still. Okay, so let me come to this second point, variational formulas. Let me free this space, perhaps. So, variational formulas. So, for the moment, we forget about everything which I said before. We shall remember about that at the proper moment. So, suppose I have now a Riemann surface. Let's denote it L, a compact Riemann surface of genus G. And, well, introduce the set of standard objects, choose some Tarelli marking, the basis, canonical basis of cycles, canonical basis, and denote by V alpha the normalized holomorphic one forms. So the normalization, the coefficient I am going to choose to be equal to 1. So integral over A alpha of V beta is delta alpha beta, and B alpha beta is the matrix of B periods. B alpha V beta, symmetric matrix with positively defined imaginary part. Now, suppose I want to vary the moduli of my Riemann surface. Of course, we can do it in many different ways. The most canonical way is to take some Beltrami differential and start, well, varying the structure, the complex structure on L using the Beltrami differential. Then in any textbook we find the following formula for the variation of the matrix of B periods. Delta mu of B alpha beta is what? Is the coefficient I always forget, so it's double integral over my Riemann surface of V alpha, V beta times mu. You see, well, what we have here, well, it's a little bit sloppy. So here we have one form, Beltrami differential is one form with respect to Z bar minus 1 with respect to Z. So what I get here is one form which I can integrate. If I can put wedge here, but let me skip it. Now, somehow what is slightly less known? So this is elementary proof of this theorem we find in any textbook. Slightly less trivial thing is how to change my differential V alpha. Well, for that, the formula looks like that. So here we are in the context of this Gauss-Manin connection. When we have the Hodge bundle, in each fiber we have a basis of holomorphic differentials, and we look at how the basis changes when we go along the base. And here, to write an analytical formula, well, first of all, we need to say what to do with the with the argument. So we can take the Fuchsian uniformization of our Riemann surface, fix the point in the upper half plane, and then the formula will look like that. So the Fuchsian group changes, the point in the upper half plane remains the same, and then the formula looks like that. Principal value of double integral over the Riemann surface of the new object, W of Z prime times V alpha of Z prime. So what is this W? W of z prime. So here z and z prime are 2 points in the upper half plane. But of course, one can define this object just for 2 abstract points of my Riemann surface without appealing to the Fuchsian uniformization. So let me do that. So suppose x and y are 2 points of the Riemann surface. Then W of xy is given by dx dy logarithm of the prime form. So the prime form is an object which replaces the monomial x minus y on a Riemann surface. So it's a class of the diagonal on the Riemann surface times itself. But analytically, it's the following thing. It has the following set of properties. First, W of xy is holomorphic in x and in y, holomorphic one form, everywhere except the diagonal. So on the diagonal, it has a quadratic pole. As x goes to y, W behaves like that. It's 1 over, well, in some local parameter, which we call zeta, zeta of x minus zeta of y square, plus, well, here I will introduce the constant term, which I am going to need later. So 1 over 6, well, that's the standard coefficient. And this next term I denote by SB, so-called Bergman projective connection, plus etc. Since it's a projective connection, I have to indicate the dependence of the local parameter. D zeta of x, d zeta of y. So this is the behavior of the diagonal. So W is meromorphic differential, meromorphic one form with respect to x, and meromorphic one form with respect to y. On the diagonal, it has quadratic pole. And you see, this highest coefficient, of course, is independent of the choice of the local parameter. If I choose the local parameter, then this combination, well, it just gives me 1 from zeta to zeta prime. Of course, this next coefficient is going to change. This coefficient will change. And how it's going to change? It's going to change like projective connection. So what is projective connection? Projective connection is an object which, under change of variables, transforms as quadratic differential plus Schwarzschild derivative of new local parameter with respect to old one. So if I make the Möbius transformation of the local parameter, the Schwarzschild connection behaves like quadratic differential. If it's non-Möbius, then I get an extra term. And this type of behavior is called the Bergman, is called the projective connection. So this special projective connection is called the Bergman projective connection. Now, of course, well, that's not the only property I need, because if I have this kind of behavior on the diagonal, I can still add to W some linear combination of products of holomorphic one forms with respect to x and y, and this property will remain the same. So what I will also need is symmetry. So W of xy is equal to W of yx, and normalization. All that is implied, of course, by this definition. But I will avoid describing the prime form and will describe the properties of W right away. So integral over aj of W of, or a alpha of W of xy, well, let me indicate that I integrate over this variable, is equal to 0. So it's normalized one form, and of course it depends on the Tarelli marking, depends on the weak marking of my Riemann surface. If weak marking changes, then new W will be equal to old W plus some bilinear combination of holomorphic one forms. And the projective connection will also change. So these two conditions plus symmetry, of course, already a uniquely fixed W. So that's the object which stands here. This is the object which we need to write the Gauss-Manin connection for the Hodge vector bundle. Now, so this is the most canonical way to vary the complex structure. Then, of course, I can also write down the variational formulas for this bidifferential. Just maybe for completeness, I write them down also. So delta mu, suppose I take W of xy and, well, freeze the positions of the arguments in the upper half plane. Well, it's z and z prime. Then what I get here is 1 over 2 pi I, principal value, W, double integral over L of W of z, z double prime, W of z double prime, z prime. So integration goes over z double prime, of course, here, etc. So that's the most standard way to vary the moduli. But that's not the way which is suitable for our goal. So I will list two other ways to vary the moduli of a Riemann surface, which are somehow more elementary and simultaneously more useful. Because here, well, implicitly, well, when I'm working on the level of matrix of B periods, it's easy. I can take any Beltrami differential from the equivalence class and I will get the same result. Here it's slightly more difficult. I have to take the Fuchsian uniformization, look at the point, freeze the point in the upper half plane, and then I can write a meaningful variational formula. Here also. So there is quite a lot of structure involved. So let me just describe 3 more ways to vary the moduli. And the second one I'm not going to use. I just listed it for completeness. So suppose I take my Riemann surface, and let's choose some small contour on that. Contour L. Well, small, it doesn't need to be small. And take some vector field U. Vector field on L. And now let's do the following. Cut out this contour. Well, cut out the small disk contained in this contour. Turn it along the vector field with some time, say epsilon, and glue back. Then differentiate. Well, of course, the conformal structure is going to change. Differentiate with respect to this time epsilon at 0. What do we get? The formulas are going to be the following. Say, for the matrix of B periods, d by d epsilon of at epsilon equal to 0, b alpha beta is what? Is integral over L. Maybe I have to put somewhere 2 pi I, but let me skip this. V alpha, V beta times U. You see, well, what happens here? Here I have one form vector field. So I get the one form on the contour, which I can integrate. I get a meaningful result, and this result gives the variational formula for the matrix of B periods. You see, morally speaking, if I look at this formula where I have single integral, and this formula where I have double integral, then I realize that, morally speaking, this variation corresponds to the Beltrami differential, though support is on the contour, which is delta function in this direction, and on the contour it's given by my vector field. So this is what, but I'm not going to write the variational formula for the holomorphic one form. In this picture, it's just a reference, because I'm going to use this type of variation in more specific context of the variational formulas on moduli spaces of holomorphic one forms. But it's just to give an idea of what's going on. So the third way to vary. Well, but it's not a metric picture. Well, you always get a Riemann surface. You're asking, well, basically the question is, we have the transitional functions outside, we have them inside, and what happens if you switch and glue? So then you can define the new ones. It's an exercise. Anyway, this is an auxiliary picture. Let me come to more specific situation which we are going to really use. So, and here I need a pair. So now I'm going to the context of Hurwitz spaces. Let's take a pair, a Riemann surface of genus G and function of degree D. Meromorphic function of degree D, and let's assume for simplicity that F has simple critical points and simple poles. Well, especially this assumption of simple poles is not necessary. The assumption of simple critical points is actually also not necessary, but let's keep it. Now, if I have this pair, then I can use this function f to realize my Riemann surface as d-sheeted covering of the complex plane. Right? So then I take a complex plane, Z, and I take d copies of CP1. I'm drawing now what is called the Hurwitz diagram. So here is CP1, here is another CP1, etc. Now, these vertical bars, they denote the branch points. Here is. So what are the branch points? From the point of view of Riemann surface, these are critical points of my function f, or what is the same, zeros of the differential df. These are the branch points. Or there is always duality in the terminology. You can call the branch point the point of a Riemann surface, or the projection of that on the complex plane. So let's call the point of the Riemann surface a ramification point, and we denote them by x1, etc., xn, where this number n can easily be found from Riemann-Hurwitz formula. And the values of them, so zj, which is f of xj, these are the critical values of my function f, will be called the branch points. Now, in this picture, function f gives me projection of my Riemann surface to the complex plane. And here I have points x1, x2, etc., xn. And their projections on the complex plane are z1, z2, etc., zn. Now, let's ask the following question. Suppose I have a holomorphic one form V alpha on my Riemann surface. V alpha of x. Now, let's ask what happens if I take this object and differentiate it with respect to the branch point. So this is a standard, somehow standard context of the Picard-Fuchs equations for the periods of holomorphic differentials, right? And then I have to say, of course, what do I do with the argument of my holomorphic differential? And of course, the natural way is to assume that the f of x, so if that the projection of the point x of the argument of the holomorphic differential is fixed when I differentiate. So the argument is fixed, and the rest, so I'll write it like that f of x remains constant. So locally, of course, I can consider this differential as a function of the variable z on the base, right? So what's that? And to compute what this is just one-line computation. To compute, well, to prove these variational formulas, you need to read half of the graduate course in mathematics, or half of the book in Teichmüller theory. To prove this formula, you don't need anything. You just need to differentiate a little bit. And maybe I show how to get this formula. It's quite instructive. I'm not sure, actually, it's the way Rauch originally did that. By the way, of course, these variational formulas are called Rauch variational formulas. Of course, Rauch didn't have any idea about Beltrami differentials, etc. He was working in the branch covering picture. But the derivation for these formulas he had, I was unable to understand. So I think these days many people realized how to do it directly. And so the proof is, so first let me write down the formula. The formula will be like that. I'm not sure again about 1/2, hopefully. Well, let me write it in terms of residue. Residue at y equals x j of the following thing: v alpha of y, w of x y divided by df of y. So you see, pure local formula, no integration, nothing. With respect to y, what this is? One form divided by one form. So I get one form, and you see df, well, y is a simple zero of my differential f, of differential df. So this form has pole of degree 1, so it makes sense to take the residue. Actually, the same formula holds if the branch point has high order multiplicity, but the proof is slightly more involved. For the case of simple branch point, it's really trivial. So let me just indicate the proof for completeness. So proof. I have to prove something, and I prefer to choose something simple, like this formula. So let's look locally. So which kind of object is that? First of all, clearly it's holomorphic everywhere outside of a small neighborhood of the point xj, because V alpha was holomorphic differential. If I take any point on my Riemann surface except xj, then I differentiated the holomorphic object with respect to the argument. It remains holomorphic. Nothing happens. The bunch of local parameters, how the set of local parameters on this Riemann surface looks like. Everywhere except the branch points, I can take z as a local parameter. And in the neighborhood of x1, for example, the local parameter is equal to square root of z minus z1. And also infinities, I have to think about infinities. Let's say take the point infinity 1 sitting on the first sheet. Then, of course, the local parameter is equal to 1 over z. So, And you see all these local parameters, they are independent of Zj except one, except the local parameter in the neighborhood of Zj. So something interesting may happen in the neighborhood of Zj. Everywhere else, nothing happens. So I get a differential, which is holomorphic everywhere except Zj. And what about the periods? V alpha is normalized in a standard way. So the period number alpha is 1, all other periods vanish. So when I differentiate it with respect to Zj, all periods vanish. All A periods vanish, of course not B periods. So I will get something some differential which is normalized to have all vanishing A periods, and then it's either 0 or it cannot be holomorphic, right? Because the holomorphic differential having all vanishing A periods is 0 by Riemann bilinear relations, for example. So the only thing we have to realize, we have to understand, is what is the behavior of V alpha in the neighborhood of Zj after differentiation. So let's look at the local Taylor series of V alpha in the neighborhood of xj. How does it look like? Well, we have some coefficient a plus b times square root of z minus zj plus etc. d square root of z minus zj. Right? So I can write it down in terms of dz. So what's that here? This is dz over 2 square roots of z minus zj. Right? So if I write it down now, I get, what do I get? I get a over 2 square root of z minus zj plus b over 2, which I don't really need, plus etc. dz. Now, when I differentiate this object with respect to zj, keeping z fixed, V alpha derivative with respect to zj. What's that? Well, that I have to differentiate, right? So I get here minus 1/2 and another minus. So altogether, a over 4 square root of z minus zj cube plus something dz. And now I go back to my local parameter, well, to the proper local parameter. What do I get? I get here a over 2 z minus zj times d square root of z minus zj. Oh, and plus higher order terms. So what do I see here? I see here that I have a quadratic pole, right? Because the local parameter is square root, so this is quadratic pole. And the highest, well, this singular, the coefficient in front of this singular contribution, coefficient a, is just the coefficient of my holomorphic differential. So I can write this formula roughly like that. D by dzj of V alpha. Well, so this A I can denote, say, by V alpha at zj. So when I'm writing it like that, then I understand it in this sense, right? The value of the differential at the point is, of course, ill-defined, but it means that I well, divide out the distinguished local parameter and then compute the value of the function at this point, or xj. And here, so what did I get? I got meromorphic differential with quadratic pole. I have to put 1/2 here because of that. And the highest order coefficient is 1. So basically what stands here is w of x xj, where again the differential w, well, I take its value at a point, dividing out the d of local parameter first, and then computing the value. But in invariant terms, what I got here is exactly that. Here there is no reference to the local parameter, nothing. So it's nothing but that formula. So the appearance of w here, it appears because it has quadratic pole on the diagonal and well, and has all vanishing a periods. And when we differentiate the holomorphic differential, then this is exactly what we get. So the proof of the Rauch formula here is completely trivial. Right? Now, how to derive the formula for the matrix of B periods, the variational formula? I just take that and integrate over the cycle B beta. So integral of this over some cycle B beta gives me, well, in the left-hand side I get, well, of course, you see, I have to say something. I have to say that I assume that my cycle B is independent of the branch points. But of course, I can always choose the B cycle such that its projection to the Z plane is remained fixed under differentiation. Differentiation is completely, deformation is completely local here. It's not. So when I integrate the left-hand side, I get d by dz j of the matrix of B periods. And here, what do I get here? If I integrate w with respect to x along some B period, then it's quite well known, the property that if I integrate w along a B period, then I get B period number beta. Then I get 2 pi I times holomorphic differential number beta with respect to the second argument. That's an easy property. So I get nothing but this formula, residue at y equals xj. Here I have to put 2 pi I. Yeah. Of B alpha V beta divided by df. This is a nice formula, purely local. I get one form times one form divided by one form. I get meromorphic one form, take the residue. That's it. That's the variation of my matrix of B periods. Well, this is, of course, the version of the Picard-Fuchs equations. If I take, say, elliptic integrals, start differentiating them with respect to the parameters. It's the Picard-Fuchs, and this is the advanced version of the Picard-Fuchs equations. Good. So that's the third way to vary the moduli. And I need also the fourth one on the fourth space. You see, what is the advantage and disadvantage of this method of varying the complex structure comparing, say, to the canonical one? The advantage is that the formulas are much simpler. You don't need to integrate anything. You just take residues. The disadvantage is that you need an additional structure. Here I have only the complex structure of my Riemann surface, and that's all. I take Fuchsian uniformization. I write down my formulas. Here I need a function, so I need an additional structure. Here I need, well, here there is a lot of additional structure. There is a contour, so I can choose it in infinitely many ways. So this is really quite a general framework, but well, there is always a price to pay. So another, and the last version of the variational formulas which I want to describe, it also requires an additional structure. And this is the so-called space of holomorphic differentials. So number 4. Actually, there is quite some similarity with the Hurwitz spaces, but there are also differences. So 4 is variational formulas on spaces of holomorphic differentials. Here I'm going to work with the space of pairs, a Riemann surface and holomorphic one form. And moreover, I'm going to fix a stratum of this space. This space has natural stratification. I can fix the orders of zeros of my differential. And of course, their sum is going to be 2g plus 2. Let's denote them m1, etc., mr. g plus 2. And x1, etc., xr are zeros of W. So the divisor of my differential is sum of m j x j. You see, it's not a coincidence that I denote the zeros of W by the same letters here as the zeros of the function f, as the critical points of function f. Because in this context, I can think of a point of a Hurwitz space not as a pair Riemann surface meromorphic function, but as a pair Riemann surface and exact meromorphic one form, df. And then these branch points are just zeros of df. Of course, well, here df has singularities and it doesn't have periods. The holomorphic differential, well, it does have periods and it does have zeros, except the case of the genus 1. So let's denote this by hg m1, etc., mr. It's the stratum of this kind. So what is the dimension of this stratum? Well, suppose, so dimension, if we take all mj to be equal to 1, then of course the dimension, to get the dimension, we add up the dimension of the moduli space and the dimension of the space of holomorphic one forms on a given Riemann surface. So I get 3g minus 3 plus g, 4g minus 3. Right? Dimension is equal to 4g minus 3. It's the dimension of the largest stratum. Well, when I start merging zeros, if I merge 2 zeros, then dimension drops by 1, etc., etc., etc. Right? So what are the local coordinates? You see, in this setting, in the setting of Hurwitz spaces, we know that we can use the branch points as local coordinates. Of course, globally, well, something may happen, but locally, well, when I say how the sheets are glued together, then the positions of the singularity, the positions of the branch points determine the conformal structure completely. What are the local parameters here? Well, local coordinates. Local coordinates. Well, these are so-called homological coordinates. Let's denote by Lj some basis in the relative homology group. H1 L with respect to divisor of W. So which kind of, what is the basis here? The basis of absolute homology, so A and B cycles, plus contours between the zeros of my one form. So I take, say, x1 and integrate to x2, x3, etc. And I get the basis in the, well, these are just contours. then I should of course take my one form and integrate over these contours. Then I get a bunch of homological coordinates which are equal to integral over Lj of my one form.